Hello, friends. Have you ever copied a number from one system to another and the value came out completely scrambled? Like the number you sent and the number that arrived just don't match, even though nothing was lost. That's not a bug in your code. That's something called Endianness. It's the order in which a computer stores the bytes of a number in memory. And in this video, we're going to break down exactly what it is, why two different orders even exist, and where it quietly breaks real code. Let's get into it.
All right, let me set this up properly. Look at this number, 0x12345678. In hex, every 2 digits is 1 byte, so this whole number is 4 bytes long. That makes it a 32-bit integer. Now, here's the thing. Memory in a computer isn't one big slot. It's a long line of addresses, and each address holds exactly 1 byte. So if I want to store a 4-byte number, I have to spread it across 4 memory slots. And that's where the question shows up. Which byte goes into the first slot? Do I start with 12, the most significant byte? Or do I start with 78, the least significant one? Both choices work. Both are valid. And that single decision is what Endianness is all about.
Let's start with the more intuitive one, big-endian. The name comes from storing the big end of the number first. Big end meaning the most significant byte, the byte that carries the largest value. So in our number 0x12345678, the 12 on the far left is the most significant byte, and the 78 on the far right is the least significant. In big-endian, we store them in memory exactly the way we read them. 12 goes into the first address, then 34, then 56, then 78. The reason this feels natural is because it matches how humans write numbers. When you write 1234, you write the thousands digit first, not the ones digit. Big-endian does the same thing with bytes. Networks use this order too. It's literally called network byte order, which is why every packet flying across the internet follows this convention. Now let's flip it. Now look at this, little-endian. Same number, completely opposite order. Here, the little end goes first. Little end meaning the least significant byte, the one carrying the smallest value. So 78, which was at the far right of our number, now sits in the first memory address. Then 56, then 34, and finally 12 ends up last. The number is stored in memory backwards compared to how we read it. And here's the surprise. This is the order your laptop is using right now. Intel and AMD processors, which power almost every Windows and Linux PC, are little-endian. Most ARM chips run in little-endian mode too, which covers your phone, your tablet, and Apple's M-series Macs. So the dominant order in consumer computing is actually the one that looks wrong to a human reading it. Which raises an obvious question. If it looks backwards, why do we even use it? Let's answer that next. So why would anyone design a system that stores numbers backwards? It actually solves two real problems. Look at the left side. In little-endian, the least significant byte sits at the lowest memory address. That means if I have a 32-bit number stored at some address, and I suddenly decide I only want the bottom 8 bits or the bottom 16 bits, I just read fewer bytes from the same starting address. The pointer doesn't move. No shifting, no recalculating. The small version of the number is already sitting right there at the front. Now look at the right side. When the CPU does arithmetic, adding, subtracting, multiplying, it always starts from the least significant byte and carries upward. Think about how you add two numbers on paper. You start from the ones column, and if there's a carry, it moves left into the tens. The CPU does the exact same thing, just with bytes instead of digits. Little-endian lines memory up in that exact order, so the processor can stream through it front to back without jumping around. Big-endian wins on readability. Little-endian wins on how the hardware actually works. That's the whole trade-off. And once you have two valid orders out in the wild, you have a problem, because sooner or later, they have to talk to each other. Now let's talk about where this actually bites you. 3 places. First, network transfer. Imagine your little-endian laptop sends a number to a big-endian server.
You write 0x12345678 in your code. It leaves your machine as 78563412. The server reads those bytes in its own order and sees 0x78563412, a completely different number. This is exactly why every networking standard mandates big-endian as network byte order. Functions like htonl and ntohl in C exist for one reason: to flip bytes between your host's order and the network's order every single time. Second, file formats. When a program writes raw bytes to a file on a little-endian machine and another program reads that file on a big-endian machine, the numbers come out scrambled. That's why proper file formats, PNG, JPEG, ZIP, even WAV, explicitly declare which endianness their fields use. They don't leave it to the operating system to decide. Third, typecasting in code. Look at this snippet. We store a 32-bit integer, then cast its address to a char pointer and print the first byte. On a big-endian machine, you get 0x12. On a little-endian machine, you get 0x78. Same code, same value, two different answers, purely because of how the bytes sit in memory. This is the kind of bug that compiles fine, runs fine on your machine, and silently breaks the moment your code touches a different architecture. All right, let's wrap this up.
So here's the whole thing in one frame. Big-endian stores the most significant byte first. It reads the way humans write numbers, and it's the standard order on the internet. Little-endian stores the least significant byte first. It looks backwards, but it matches how the CPU actually does math, which is why almost every device you own runs on it. Neither one is wrong. They're just two valid choices for the same problem. The trouble only shows up at the boundaries, when your code crosses a network, opens a file written somewhere else, or pokes at memory through a pointer cast. That's where you have to know which order you're dealing with. If this cleared things up for you, hit that like button and subscribe to Webronaq. We've got more videos coming up that break down exactly this kind of low-level concept in plain English. Thanks for watching, and I'll see you in the next one.